Here we're going to show the wireless bipolar Tesla coil system. This consists of 3 phases of pancake coils driven from an alternator with secondaries above and below that 266 primary, as we refer to it. The 266 primary has measurements imposed on it from these initial meters. When we turn the device on, we note the action of those meters from rotation alone, and then we energize the field. We're going to energize the field we're going to send 8 volts into the field. We're going to turn the device on, note that, and then we're going to immediately go to 8 volts. Note the operation of the Tesla coil system. The Tesla coil system has 2 arc gaps. Unfortunately, we got a main bar arc gap of those rectangular copper alloy bars, and we got a spherical arc gap there. The spherical arc gap is going to be given to the weaker bottom coil phase, which generally receives less voltage from the system, and the top coil system will be given these arc bars here, and the front Tesla coil system over here, the one to the left, will be given the higher voltage input from that wireless action. So we'll get in there now, immediately turn on the motion, and we'll turn on the field and come back and look at some of the conditions. These things take a minute, but we will explain. Oh my goodness, what's happening? Well, we explain here then, which should be visible in this lighting. We do have some lightning coming up. I don't know if you can do, we turned that one fluorescent out. That lighting for the meetings looks good. We'll go in there and energize the field. Or turn on the motor. Hey. There's the action of the inputs before the field is turned on. We're going to put an 8 volt field in there. And immediately upon that 8 volt field, the Tesla coil should start working. We're concerned with these values here, which look controllable. On the outside we only got 5 some amps, and the phase amperages are relatively low at 1 to 3 amps, but we got spectacular voltage deliveries. Phase 1, 13 volts, the yellow meter. Phase 2, a high fluctuation of 48. Phase 3, even only reading 22 volts. Now we look at the operation of the gap. Here's the operation of the primary gap. Secondary gap, I do not imagine will fire right yet. You just see no firing on the secondary gap. Now we'll look at the terminals. Terminals have quite a large firing. Don't seem to want to focus for some reason. Let's take that out. Okay, there's the firing of our top two terminals. Let's see if we can negotiate a stand here. We had this problem last time. Now we're going to bring a neon in the vicinity of those two. Handheld neon. Three different bolts. This is the helium bolt. Direct signal action. This is the xenon bolt. And this is krypton bolt. And now it should show sufficient supply. Now we're going to try to finish here. I'm going to show side two. The wireless aspect, which can't be shown. We will try. Going to lift that top coil off its primary and try to capture that. Can't really get it wide enough. Yep, there, we'll try there. Operation ceases when the top coil is removed. It is entirely a wireless custom coil. And one of the problems with it all, of course, is getting that other gap to work. We'll finish out here and look at our inputs. Gap's been running appreciably a long time. There's no real problems. There's our input for that action. And we're content to see that the stator lines are only under 5 amps. The phases are 1.6, 1.5, 2.6 on the top layer. And we got fluctuations of voltage. The 10.9 to 12 volts is what's actually sent in. Phase 2 showing some 55 volts, and phase 3 is showing a medium 23.6 I thought I saw. Okay, well, that should be it for now. the durability of this machine, continue its performance over this time period. Seems that it works in a well and constant nature without associated breakdown from overheating of arc gaps, etc. Thank you.